So I have just uploaded a recording for the last part of the multiple imputation. So if you are interested, you can check in YouTube. I will just move on to chapter 6, fractional imputation. So this is okay. Oops. Okay. So this is more about frequentist way of frequentist approach to imputation. And starting point is to think about view Monte Carlo EM as an imputation. And if you recall that Monte Carlo EM is a frequentist approach to imputation, but the convergence is not guaranteed for fixed M. And also the E step can be computationally heavy because you apply Monte Carlo sample, you draw Monte Carlo sample for each iteration. So here's a new approach, similar but slightly different approach. So suppose I have H initial density proposal. So this is sometimes called proposal density, where I can generate samples, Monte Carlo samples. And then idea is this is my target. So this is the target distribution. This is proposal. So basically, given M sample, right? Given M samples from H, given M samples from H, I can evaluate the ratio of the at each point, and then normalize it. So this one is essentially normalization, right? And then this weight is applied. The weights are applied to the to each sample. So for example, if I have M samples, right? Then so for unit I have a J equal to 1 to M. So then I have M samples, and then I have weights assigned. But the weights are essentially this one, right? So essentially kind of a ratio. So this is okay. The weight itself is the ratio yi star j delta I eta hat divided by h yi star, right? And then normalize it. I'm sorry? Eta? H is a general. So we'll discuss H later, but let's assume that H is given, then basically this is the weight. And then we normalize it. So then if M goes to infinity, it goes to expectation. And the expectation is with respect to H, because the samples are generated from H. So then so basically this is a numerator is okay. How can I write it? Well, this is more like a expectation of the G, Y, and then the ratio, impotence weight. H and H, right? So basically we because we have a G here, and then the weight is this one. So we just take the expectation of this whole thing, and then denominator is just used to make it sure that it's expectation, conditional expectation. So then this guy. So the numerator, okay. We are taking so this one. Then what happened? We end of the day we get a cancellation, right? So we have a cancellation, and then denominator is the marginal density, right? So the denominator becomes equal to the marginal density of the observed data. The numerator is computing the integration over the joint density. So joint density divided by the marginal density is a conditional density. So that's why you get this conditional expectation. Okay. So that idea is actually is kind of a technique in the Monte Carlo sampling. So impotence sampling idea, impotence sampling, and then the denominator is a proposal distribution, and the numerator is the target distribution. Interesting part is that we do not, even if we are interested in generating. So originally we are interested in generating imputation from this conditional distribution, but in computing the fractional weight, turns out that this is, so originally this is target, right? This is your target. This is your proposal. So remember, proposal is where you generate samples from, right? You generate sample from H using H. What is target? Target is your goal, right? What you really want. What you really want is this target distribution, which is the imputation distribution, F missing, given, observed, right? So there's a discrepancy, but still we can view this as a Monte Carlo approximation so that we normalize it. Then nice thing is that the target distribution has a joint, because target distribution is the conditional, and conditional is a joint divided by marginal, and the marginal part is this one, has nothing to do with the imputation, right? So you actually is basically constant for I. So that means this marginal distribution essentially cancels in the numerator and denominator, and so your fractional weight is actually using the joint density only. So this the right side is, so right side is more difficult to compute, because when you compute the conditional expectation, you need to compute the integration, right? And the left side, you don't have to compute the integration. So that's one computational advantage. Okay. And so this idea actually is applicable to develop the EM algorithm directly. So you have a imputation. So you generate imputed value from H, and then you compute the weight, fractional weight, using the ratio of the joint density of the model given the proposed density, evaluated at the missing data, right? Evaluated at each sample, Monte Carlo sample, and then M step, you basically compute the weighted log likelihood. Okay, where the weights are computed from the weighting step, and maximize it over eta. So that is M step. And then one thing you may want to check is that when this W, some of the so weight is between 0 and 1, and some of them over J will be equal to 1. But some cases, if the denominator is too small, something like that, then you will have a very unbalanced, right? So that means your particular initial point. So that means your sample point is not really good. So here's a, for example, this is your target, okay? And but suppose your proposal is this, for example. Then, well, this is not a really good example. So let's do it this way. Suppose this is your target. Oops. Suppose this is your target, and your proposal is the other way. Then the ratio, for example, here, so this is H. So if you choose this one, that means that you are kind of wasting in the right side, right? You throw a sample here, which is not really necessary because you have a low chance of getting the target, right? While here you are kind of lacks resources, right? Lacks samples. So that means your H is not really good. Your H is not really good approximating the target, right? So then basically you can use this weight, fractional weight, as a kind of a diagnostic tool to examine whether your H is really good or not. So if that happens, then you may choose different H. So one way is to use the current parameter value to compute the conditional distribution, and then use it as the H and go to step 1. Otherwise go to step 2 instead of step 1. Okay. Why? So why is this? It's good to go to step 2, because if you go to, so from here you go to step 2, so or step 1, right? Or step 1, where usually sampling is expensive. Okay, computational sampling is expensive. Why? Because when you sample, you need to draw a random number, right? First, and to draw the random number, that means you need to call some function, but that's usually heavy computational cost, expensive. While the weighting itself is not really expensive. Weighting is just a function, right? You just compute it easily, but the imputation step is expensive computationally.
But so if the weight is too large, so
Okay.
then you are thinking that to be conditional of missing given observed. So then you need the knowledge of this conditional distribution.
I'm sorry?
So then you need this conditional distribution. The purpose of this that if we do not have the conditional of y is given y observed, then we use the proposal. So you use the proposal density. But so if weight is too large, so when the proposal density is not good, then do you need the knowledge of conditional distribution of y is given y observed? Because you are fixing that to be h y I.
Well, so I mean, let's be real. Suppose I know that, so F is known, right? F is known. So I know the model. I have a model, and so I can compute the conditional distribution. The only problem is that I don't know the parameter in the conditional distribution, right? So F is known. So I'm accepting model. I just don't know the parameter, okay, for imputation. So what should I do? Okay, well, I will just pick arbitrary parameter, choose arbitrary parameter, start from there. But the weight will actually tell you, right, whether your current parameter is good or not. So if you could actually update parameter every time. That's one way. But the message here is that you don't have to. I mean, if you update parameter every time, that's essentially the same as EM algorithm. But the point is that because the computation is expensive, the sampling is expensive, so we can save some time by skipping step one. Some time.
Actually, I think the question is more like if we want to choose a good proposal distribution, if we want to choose a good edge, then we need to know something about the target distribution.
We don't know, so right, the choice of H is a little bit so not really clear. I mean, this is general for given H, we can do this way, but
yeah, but I think the point here is we do not need to know the exact conditional distribution. We just need to know where it's maximal, where it's most, and then what the support, and then we can design edge on that support.
But in the fourth step, so basically, if you go again, you are simulating from F y is given y observed and eta hat t. So then to simulate from that, you need the knowledge of the conditional distribution, or at least how you can simulate from that, right?
yeah, so simulating, if this one is easy to simulate, then we don't really have to go all these steps, right? But sometimes this is not really easy, and you may want to use so suppose we have an example later, but this is not always easy to generate samples from directly, but it's doable. I mean, you can do MCMC, for example, in the GLMM. Generating from this one requires MCMC algorithm, right? And that's the whole motivation. This is expensive. Generating from this is expensive. So if this is not expensive, then really we don't really have to follow all these steps. Okay, well, let's move on.
Extremely small W weight.
Hmm?
So here we know that we have some ways in sampling from H if we have large W.
Right.
Then what if we have extremely small W? Will that be a problem? We have some-
Well, small. Well, I think small. So extremely small means you just a downweight. So downweight the imputed value is not really big deal, but the problem is one way some of the few one or two imputed value may dominate. I mean, still you can use that, but this is just to improve the efficiency of estimation. Okay, we'll see a lot of examples later, and probably it'll be more clear later. So imputation step and weighting step consist of E step, and then interesting part, imputed values are not changed for each EM iteration. So that's actually interesting part, because imputed value here, if you do this way, this is fixed. I mean, after step one, they are fixed, but the weight depends on T. So the weight depends on T because the eta hat depends on T. So then the computation itself for weighting is easy, efficient, and also convergence is achieved because imputed values are not changed. So MCEM, for example, doesn't converge because you every time if you generate the Monte Carlo sample at each t EM iteration, you will never achieve convergence, right? Unless you increase the m. So the idea is this is fractional imputation is one way to achieving the convergence checking and get efficient estimation. So that means because imputed values are fixed, it converges to something. And for large M, this convergent one converges to MLE. Okay. And then interesting part is that this weight. So once you do this weight is a kind of a tool to compute other estimators. So the weights are here constructed from EM algorithm, right? From this EM algorithm, you use this. I'm sorry, you use this method to construct the data, Monte Carlo sample and weight, and then use that to compute other things like this. So you can input, right? You can input the fractionally imputed data set to estimating equation and solve it. That actually implements what? So this guy actually implements the conditional expectation of psi y given data. It actually implements automatically. And then this one, basically this way take care of the conditional expectation, right? Because this is kind of a finite sample using finite Monte Carlo sample to approximate the conditional integration associated with the conditional expectation. Okay. So this theorem is essentially a version of the EM algorithm convergence. So we use the log. So this one essentially approximates what? This one approximates the Q eta given eta t, which is the conditional expectation of the log likelihood. Eta given data and eta hat t. Okay, so you have a log likelihood, right? You have a complete sample log likelihood, and take the conditional expectation, and then remember the theorem 3.1, whatever in the theory of EM algorithm, we basically showed this kind of result, right? So whatever we maximize this Q term with respect to eta will increase the observed likelihood. So that's what we learned, right, in the class. So basically the same argument holds for non-parametric, the Monte Carlo version of the EM. So this is kind of Monte Carlo version of the same theorem. But because our Monte Carlo sample doesn't change over t. So the weight changes, but the Monte Carlo sample doesn't change. So that's why we can achieve the likelihood increase.
Okay. So also that's why you need another condition one, right? Because due to the finite n, so the Q star is not exactly equal to the condition expectation below, right?
Right.
That's why you need the condition one. So based on condition one, you can derive condition two. And the condition one can be, so it's automatically satisfied in the optimization, right?
Exactly, right. That's the M step. M step basically satisfies this, right? Because we maximize the M step. So okay. So remember when we prove this original theorem, we use Jensen's inequality. So we are actually, it has the same structure. So basically this is the basically plays the role of the expectation. Okay, conditional expectation. T. So this fractional weight and the summation basically is implementing the conditional expectation using Monte Carlo. Okay. So that's basically what it's doing. And then the log of the expectation can, if you switch, right? This is a concave, log is concave function. So you can apply Jensen's inequality to get this inequality. And then you can now exchange log and expectation goes outside here. And then that's basically the Q star term. And because of this, so by definition, so one, right? This is one. One implies the Q at task. P plus one maximize Q star. So it actually has a increase, likely to increase. Okay. Yeah.
If you keep on changing the sample y star miss instead of fixing in state one, this monotonicity of Q function won't satisfy, right?
Right.
Because
So,
in C.
right. So that's right. So this is only applicable to when we fix the Monte Carlo sample.
And if you don't fix that, this method is equivalent to MC.
But still,
I mean, just for illustration, like then it would, the monotonicity will not satisfy, right?
right.
But how this can show the convergence of the algorithm?
Huh?
How this theory implies the convergence of the algorithm? It says that the I star will increase,
Okay.
but how this implies the convergence of the eta hat T?
That right. That's the same story. I mean, so yeah, I think that's actually the what we covered in chapter 3. I don't know whether I can find it, but that is actually quite difficult problem. So it only shows the monotone increase, not really, doesn't really prove the convergence. So we do need more assumptions. Like, so it is basically the argument in the paper is that, so Jeff analyst paper 82 or 83. So the argument is that it's a bounded above. So you have a bounded above and then monotone increase so that this sequence will converge and then under some conditions on this like function you get convergence or something like that.
Basically, you need a good curvature for the I star. You need some good curvature property for the
Yeah, I think so. Yeah, right.
I star.
Yes.
Yeah, but that's probably typically assumed on the population level. So this is fix the imputed samples, like the finite samples.
Yeah.
Case.
I think this is really try to, the motivation is to make the computation easy. I mean, rather than, yeah, so. And try to provide different framework. At the time, multiple imputation was so kind of pushed in the community, and there's some resistance about multiple imputation, and I was one of them. So I was able to I kind of devised a way to do something other than multiple imputation. So this is one way. So you can see from now on we'll have a lot of examples. We'll see. You can see that it's actually very convenient because all you have to do. So, for example, here the problem is we want to generate y from y given xi and delta equal to I. Okay. Not missing a random. This is not missing a random case. So in this case, we know this is proportional to y given x, which may depend on zeta, and then it's a 1 minus, right, delta, so pi x y. Sorry. So let's do it. So this is and then probability delta equal to 0 given x and y. Okay, so and then this is we have a parametric model. So then we have this is kind of a model. And suppose you have an estimate. We do not necessarily know the parameters at this point. We can just use EM. So this is basically what we want. So originally we are interested in generating, imputed values from these conditional distribution. Okay. So two problems. First of all, we do not know the parameter in general, right? We need to estimate it from the data somehow. And secondly, generating from this one itself, this conditional distribution itself is unknown. We don't have a name, right? It's just a product of the two known function, density function. So then how to really compute it and what's easy way. So one way is use the fractional imputation using this one as the initial h. Okay, so now let's use an initial parameter zeta hat 0 and use this one as an h. So this is my proposal distribution. Okay, and then from this I can generate. Okay, and then now I have m values, and then these values are applied to this function, so that we can construct the fractional weight using the current parameter. So this is h. Basically, this is h, right? So this is h actually yi star j. Because we want to evaluate it for each yi star j. So I for each one, I evaluate it, and then numerator is f, the target, right? The target. So that is this target, which is a closed form, right, of the constant. So this is actually the weight is actually is a closed form. You can just compute it by just programming, right? So then you really don't have to worry about anything as long as you determine. So this is kind of engineering. So I try to make it more engineered way. So we just generate it from something and then compute the ratio and normalize and apply to your data. So that is the basic, and then iterate. So that is so weighting part is a most tricky part, but is a very engineered way, engineering formula. And then using the imputed data and the fractional weights, the M step is automatic, same thing, right? You just apply the fractional weight to the score equation and solve for parameter to update it. Okay. So that is basically the idea. So now let's suppose I consider GRMM. Remember, if I want to do it GRMM using the usual EM algorithm, it will involve MCMC method, so which can MCMC for each step, so which is very difficult, computationally very expensive. So here's if I use fractional imputation, let's see how it goes. So the idea is the same. You have a level 1 model, level 2 model. So this is your target. So this is your target, and A is missing data. So I use the red color A to denote the unknown parameter, to denote the missing data. And so I want to use the imputation approach, fractional imputation approach. And one way you can do anything. You can actually, I would do, so the one inefficient way is just to use this one as a H. Okay. If you use H, or you can use something called variational inference. So basically, you can use Kullback-Leibler measure to minimize, right? To minimize the Kullback-Leibler divergence measure as a H. Because then you will have a very good approximation of the target. And so, but no matter what, in this case, if you use this one as a H, then weight is just the likelihood part, an F1 likelihood part. Right? Because this is the F1 times F2 divided by F2. Where F2, so this is, I mean, the product of F1 and F2 divided by F2, then this is your weight, right? And then M step, same thing. Okay.
For the end step, why did you choose those simple ones that are here? Oh, so your model has two parameters.
Right.
Second one, yeah.
Okay. Yeah, same story here, right? I mean, same story here. We have two different parameters, and but still we apply the same imputation data. So fractional imputed data to solve the equation.
So for the example one.
Okay.
So for example one, right. So this
Here?
this is fixed example.
Okay, here.
So the equation 3, so next page, the equation 3. So this, the equation 3 is free of theta.
Right.
Expression of theta.
But here is a kind of implicit here.
Right. So theta is, but that theta is big.
Right.
So this is because of the log likelihood is the additive of these two parts, right? And if you take derivative with this.
Right.
The theta here.
Okay.
Okay, and the first one is 3/5, so it's basically easy to solve.
Okay. And now, so it can be applied to any. I mean, EM algorithm itself is very general, right? And so basically we can apply the same. So fractional imputation to any problem that EM algorithm can be applied in a computationally feasible way. So that's basically the motivation. So measurement error model, remember, so this is y given x, and instead of observing x, we observe z, which can be highly correlated. So x is the accurate covariate, and z is the covariate with measurement error. And then you can see that if you know the accurate x, right? If you observe accurate x covariate, then this noise version is not necessary in explaining why, right? So this is a kind of a assumption. And then, but without x, C is still useful in explaining why. Right? That's the typical assumptions for any Z mismeasured. So and then yeah.
So, in general EM, where in the E state you do not need the Monte Carlo state. So in those cases, I mean, fractional imputation would not be helpful, right? Because we have the conditional distribution, we have the conditional expectation also in closed form. But in cases where those are not tractable,
Right.
in cases where we need Monte Carlo state in E state in the EM, there we can faster by using fractional imputation.
Sure. Yeah. Right. I agree. So the E step, if for example Gaussian multiplied normal and things like that, in that case, conditional expectation is a closed form, right? Then you have an exact solution. I mean, exact E step, no Monte Carlo. But this fractional imputation is actually a Monte Carlo, a Monte Carlo method, and without using MCMC. So we introduce the concept of the weight, fractional weight, to reflect the approximation of the Monte Carlo sample. So you can view it as a computational tool. So for imputation and computing the Monte Carlo expectation.
So for the generalized linear mixed model example, so yeah, here. So if it's common, like we generate data from a Gaussian distribution, which is the NAPA approximation for the okay.
So yeah, right. So F2 is usually Gaussian, and then the user. I think I covered this a little bit in the previous class, but you can approximate this one as a normal distribution, right? And then that is essentially Laplace approach, and that's usually reasonably good. But I think.
So I have another question.
Yeah.
So if we use this fractional imputation, theoretically, can we control the difference between the estimator and the MLE, which is not obtainable by any order we want by choosing a large n? if we have such kind of controlling result?
Well, there may be, but I haven't really. I think the area of impersonal sampling is actually quite hard research area, but I don't really pay much attention. So I didn't.
Right, the reason I ask you this is because in some cases, for example, if we have many generalized linear mixed models, because we have a lot of responses, like gene expression, we have thousands of gene expression for each gene, we build a generalized linear mixed model. So if we use manual testing, then we need to control the tail probability of your estimate. So, but we cannot control tail probability from like the EM, the MC EM over the, we can only control the tail probability for MLE. So then we need to control the estimate we actually have and the MLE. So if the difference is small than the tail probability, then we can apply some manual testing procedure to justify this is theoretically can control positive discovery proportion, something like that.
I see.
So to study the tail probabilities, we need to control more rigorously, more carefully about the estimates.
Well, I don't have a good answer. I think it actually my idea is actually it has some Bayesian flavor. If you can view it as a prior, so H, you can use view as H as a prior, and then the fractional weight is actually becomes a likelihood because you have a posterior divided by prior, which is likelihood. Yeah, I don't. So this is kind of something I worked on, and then nobody seemed to be interested, so I moved out. I did, but there's some lot of several interesting applications. I will show you two. One is the data. It's a matching problem. So here's a. So suppose I have this kind of data. You have a two data structure, X and Y, and so you have a original sample, you have a Z and Y. And a calibration sample, you have X and Z. And then what you are really interested in is a regression of Y on Z. In this case, you don't observe a pair, Y and no, you don't have any data observing Y and Z at the same time. But you can still do inference. And here's the basically, so as long as this is these two assumptions holds. So this assumption is sometimes called non-differentiable measurement error. So Y is conditionally independent of Z given X. Okay. Well, let me so this is how we can do. So if you in this case generating EM algorithm it's not really clear, but if you use fractional imputation, it's really simple. So here's the idea. So basically we want to create the imputation here, right? So we want to do fractional imputation from this is a target distribution. So this is my target, but we can use Bayes theorem to get this decomposition. So the first one is just the Bayes theorem. Second one is the assumption for the measurement error, right? As long as you observe X, if you observe X, then Z is not really necessary in predicting, in explaining Y. So this Z can disappear, right? Okay. Then now this is my target. So how we can, so this is my target. And my proposal is this one, the first one. So because from the proposal, I can easily generate X, right? Using Z. So basically this is my training data. So calibration sample is a training data for training Y conjugate Y given Z. I mean X given Z, right? And then this becomes H proposal. Okay, so if I use this one as a proposal, then the ratio target to proposal is this guy, which is the fractional weight. And so, but I don't know the parameter, so I need to use the EM language. So basically, I use the current parameter value to evaluate the weight, and then use the weight to update the parameter. Okay. So that's one example. So that's actually quite useful in handling measurement error type problem. So sometimes two surveys, so you have a X is face to face survey measurement, and Z is say self-selected self-evaluate survey. So suppose you have a say face-to-face, you have a better accurate response, but for the same item, you can have a different measurement. That's possible, right? If you or phone survey or internet survey, right? Internet. If you use internet to report and face-to-face survey, you have a better explanation about the concept, and so you can view this as a benchmark, and then this one can be. This is kind of how to combine two different surveys, something like that.
In this example, we want to estimate the rating of the Y on X.
Y and X, right?
Can this be done by like the two-step mean square? Like treat Z as the incident variable.
So X is missing data, right? Here.
Okay.
So missing by design, something like that.
Right.
So right, so parameter, so it's actually twofold. One is to estimate the regression parameter, or we can just imputation can be another purpose. Okay. Well, let me move on to another example and then come back to this part. So this is actually, I think this is really promising idea, but was not fully explored. So I'd like to emphasize today, and then. So anyway, here's a idea. Okay, so let's assume that we have an X and Y. X is fully observable, and so we have n observation of X and Y is missing. And so Y are be the set of respondents, and we want to obtain m imputed values. Okay. So hot tag means, you can see real value. So real value means it's not really synthetic. So the opposite of the real value means synthetic. Synthetic means kind of fake. You made up some number, right? Why? So if you, for example, if you create y I hat from beta hat xi, something like that, this is not real y, right? This is something you made up from your model. But sometimes that's not really good. So for practitioners, they are really want to make sure that these numbers are really observable ones. If you use model, right? If you use model, there's always some danger. If you feed a regression, so y is age. One is still so y is age. How old are you? Something like that. You feed a regression. So if you do some weird model, you get negative value. Right? It's possible to get negative prediction. What do you mean by negative age? Nonsense, right? So really this kind of synthetic imputation is regarded as dangerous. So we want to make sure the imputed values are real value. And one way is just use observable data, y1 to yr. So idea is let's use y1 to, let's use r imputed value. So let's use m equal to r. Okay. So the problem is this, let's use m equal to r. And then try to find weight in such a way that it will approximate the condition expectation. Okay, so the problem is the weights are always, so the imputed values are always real values. And the problem reduced to computing weight. Okay. So suppose we use 1 over r, equal weight. That means what? That means it actually computing the conditional property given delta equal to 1, right? So we can still assume model. So here, the point is that you don't have to completely model free. You probably want to preserve the relationship, so then you need a model, but you still want to use the real data for the imputed version. So then basically this is your target. So because I know that y1 to yr, the real values are generated from what? Y given delta equal to 1. Right? This is my, no matter what the model is, they are generated from y through distribution y given delta equal to 1. Right? That's the true, because by definition, I mean. But so now question is, how can we connect this model with this? So how can we build a relationship between the two? Well, okay, here's a target. Here's the proposal. And are they totally irrelevant? No, they should be relevant, right? I mean, should be, so this parameter should be hidden somewhere, right? So parameter theta here should be hidden somewhere here. But how we really can see this? Well, let's figure it out. So, okay, this target can be written as this one, right? So the second equality is now difficult. Just the base theorem. Now let's move on. So the denominator is tricky, right? The numerator part is easy. The denominator is a little bit tricky. So let's take a look how to compute the denominator. Well, this is basically, so the first equality is what? So this is joint density of f, y, x, and y. And this is the conditional density of probability delta equal to 1 given x and y. I mean, this one, right? And it should have it. So then actually, and then we integrate out over. So it will over x, then it actually so becomes proportional, right? So the first equality is just the probability theory, and then second one. Now, what is fx? So we are integrating out over the marginal density of x, but we already observe x, the sample, right? Which is this one, empirical distribution. So we can actually have a formula, closed form formula for the proportional distribution. Okay. For J, right? For particular J, we have a J and I, something like this. So that means our fractional weight can be written as a something like this. Okay. So that looks very complicated. So you have a so what? Remember what is IJ? Fractional weight for missing I and using YJ as the imputed value. Okay, because I have a like so I have data 1, 2, right, and x1, x2, y1, x2, y2. But suppose I have three missing, and I have x3 here, but y is missing. Then I'm going to use y split and assign weight 1, 1, W3, 1, W3, 2, something like that. Star. Okay. So that is our idea, right? We're gonna use the borrow the donate these real observations. All we want is to compute the weight, and the weight turns out to be this form. Fine.
Here, which reference distribution are you using? Are you using like the empirical distribution of y as your reference distribution?
No, well, this is so we don't observe. If I observe y throughout the whole sample, then we just use that. But the only thing available to us is this guy.
So in your edge, right? So you use
H.
the fraction sampling, right?
Right.
The edge is the empirical distribution for y given delta equal to 1, right?
Right. This is H. So this H. So this is denominator. So this is H, basically. H, Y, J. So see the denominator, there's no I, right? Just a J. And K is just noises. And then now on the missing and random, if you look at the missing and random, then no longer depends on J. So you have a J. So this guy, J, so it doesn't really depend on I, right? So if you have doesn't depend on J here, it's just disappears, cancels. Okay. So basically you can safely remove in the fractional weight, so that you end up getting this. So basically what is the interpretation? So interpretation is this is kind of correlation. So kind of model, right? Density, right? So Fyj given Xi, evaluated parameter. So if I don't know true. So ideally I would like to right. So okay. So this would be my target density originally, but I don't observe y, right? Yi. All I observe is the yj from j equal to 1 to r. So what I did is actually I plug in, right? Compute the density, and the density is high. I give a higher weight, right? So that's one way. But the denominator, but if the particular yj is actually donate is close to other values several times, then it's more like a relative. I think if you, for example, if you use the Gaussian, right? I mean, so the numerator will be something like this. Numerator. So, okay. So you can decompose it as a mxj plus ej, right? So that means you will. So if you use ignore ej, just the mxj, that is kind of nearest neighbor imputation. I mean, when this weight will be high, I mean the exponential term will be high. When this is the closest, right? The mean function is the closest, we will have the highest weight. Okay, but there's an additional one, ej, which tells you where if the x is not really helpful, right? If the model is not really good, then you are actually giving the same weight. So suppose m is 0, I mean m is flat, then you will just have the error term. Error term will be uniform. So then you will actually give the equal weight. So it's more like a between one, right? Between the x, using x, you could actually use x only to create the fractional weight. But on the other hand, you can give the error, which is more like an equal weight. So it's kind of compromising, depends on your strength of the model. So that's kind of interesting idea, and that I think I think my intuition is that this is really close to the synthetic control method in causal inference. So this synthetic control method is very popular in Adobe the embed. So all these econometricians are very excited about this synthetic control method, which I think is kind of something doing some kind of a fractional hard-tech imputation, using X only. And I think so. I think this is kind of closely related, but I published it survey journal and nobody read the survey paper. So unfortunately, this didn't get much attention. But if you can modify this idea to publish it econometric journal, then it'll get a lot of attention, because this is yeah.
If you go to the previous 2 pages. So this page is fine, yeah. Next page.
Next page, I
So
mean,
your edge is basically a continuous function, right? So your reference distribution edge is a continuous function. The edge,
actually, y can be categorical.
right, but I'm thinking, so is this something like you have this reference distribution edge? So if you actually draw from edge, you will get something different from the observed data because it's a continuous distribution. But you just focus on those samples that are exactly the same as the observed data
Right.
and calculate the weight on those points exactly the same as the data.
Right. Yeah, so the whole idea is this fractional hot deck, hot deck using real value has a important practical importance. And turns out that if you look at, so actually here's some interesting example. So I applied very simple, this is more like a linear regression. Y given X is normal, something like beta 0 plus beta 1 X sigma square. So this is the very simple linear regression problem. And using normal error as a imputation model, okay? But the true model is a exponential. So true model is incorrect. So you know what I mean? In the imputation, I can assume normal regression. But turns out that in the simulation, I can generate actually the error term follows this exponential distribution. So it's an incorrect model. Then should be biased, right? So then if you do, so the mean part, turns out the mean part is not really, is okay, unbiased, but the proportion will be biased because the error term is incorrectly specified. But turns out that this fractional hot imputation, so they are biased, zeta 2. But fractional hot imputation still reasonably good. So very, very robust.
What is MI?
Multiple imputation. Multiple imputation, parametric fractional imputation. So we create a three method. Compute three multiple imputation, parametric fractional imputation of Kim, and fractional hot imputation. So this one turns out to be very robust. So I think the fractional hot imputation is less model dependent than other existing imputation approach, but there's something not really clear. So I think this is kind of unexplored area. Oh, time's up. Okay, I think that's all for today. We'll continue this